So we're going to talk about the behavior notation that you have seen before. What happens or what's the value of f of x when x it gets closer to certain value from one side or the other side, the right or the left, Um, and behavior to infinity for large values of x as well. So, and then we're going to talk about asymptotes. And there's, for now, two kinds of asymptotes. Vertical asymptotes and horizontal asymptotes. The second classification of asymptotes, that is the horizontal asymptotes, can be further divided into a few more. So in that situation, we may have oblique asymptotes or even polynomial asymptotes. We will see a lot of examples of it. How do we identify them? What's the criteria for it? And sort of, shortcuts to, in a way, say, that one has a horizontal asymptote that it's equal to 0. Oh, that's because that's just this value because the what's it called, the coefficients of the leading terms are the same degree, and boom, that's going to be just a ratio. I'll show you all the specifics in a minute. So, but first of all, we're going to graph rational. There's a little typo there. We're going to graph rationals and do some basic applications about average cost. You will see later. And well, so a rational function is a function of the form r of x equals p of x over q of x, where, be careful, p of x and q of x cannot be just anything. P of x and q of x are strictly polynomials, and q is not 0. All right, for example, let me give you an example of something that it's not a rational function. For example, f of x equals x squared plus 5 in the numerator. That's polynomial, that's fine. But in the denominator, what do we have? A radical. So that's not a rational function because, well, in this case, the reason why this is not a rational function is because the denominator, it's not a polynomial, it's a radical function. And if we think about the strict definition of what a rational number is basically an integer divided by another integer. That's what a rational function is. In the sense of extending this concept to functions, well, yes, this polynomial in the numerator, x squared plus 5, it's going to output integers all the time. However, the quantity in the denominator, x plus 1, will not output integers all the time. In some situations will output some irrational number like the square root of 5, like the square root of 7. There's just a few cases in which we get integer over integer, like values of x that are added to 1 output a perfect square, and there's not all real numbers. So for this reason, that's not a rational function, right? So let's cross it out. Another example that it's not, x squared plus 5 again, why not? Over the quantity e to the x, for example, yes, it looks like a ratio. I mean, it is a ratio of two quantities. It is a ratio of two functions. However, it's not a rational function because the denominator, in fact, the e to the x function is a transcendental function. It's a function that outputs decimal values. So it's not integer over integer. So sticking to the definition, it's polynomial over polynomial for now, right? Well, so this notation that you may have seen before, maybe some of you took an AP calculus back in high school and you know about limits. Well, even if you haven't, well, I'm not expecting that you know all that. But you may have seen this notation, x, an arrow, and some number or some letter. Well, we're going to go with numbers, of course. And well, we have a subscript, a plus and a minus. Well, so what does that notation mean? Well, that's a notation that you may have seen in calculation of limits, in case you have taken a calculus class before. Well, we're sort of going to talk about limits, like what's the value being approached, but we are not really going to work with the definition of what a limit is. We're not going to compute any limits. In fact, all this about asymptotes, you guys will look at again in Calculus 1 next semester in Math 150. Same thing about asymptotes, but from the point of view of finding limits instead. If you guys have taken an AP Calculus course, maybe you have an idea of what I'm talking about. Now, this is the most generic version of a function that it's a rational function. We have the function f of x equals 1 over x. So you might remember something called the library of functions. You know, you're given the graph of f of x squared, you know, the parabola, the cubic. Well, in particular here, we're talking about the function f of x equals, does anybody remember this one, this graph? What's the function f of x? What is it? 1 over x, all right? 1 over x, yes. And well, so we're going to do some asymptotic analysis here. In fact, this function has both horizontal and vertical asymptotes. Usually, most of the times actually, they will give you graphs like this, and in this case, it's our job to figure out those asymptotes. Well, let me draw them. If you guys use colors for drawing this graph, well, typically we use red for asymptotes to give us a sense of precaution here again, like a value that the graph is not supposed to touch or cross, right? Well, in some cases, it's possible. We will discuss those later. Well, so here is the thing. To link this graph with the notation above, let's see. So we have this graph of 1 over x. We have this graph of it has two tails, the tail towards the left and the tail towards the right. And well, so suppose we move along the graph from the left. So from the left, we approach a certain value. So what's the value? What's the value that we approach as x approaches 0 from the left? So if we continued here all the way, so what is the trend in this situation? What is the y value apparently being hit? Any ideas? Negative, small, negative, big. Well, actually negative really big because it's going down to negative infinity, right? Which is what is this sentence telling us here? As x approaches 0 from the left, the y value is going to negative infinity. Likewise, we can also approach 0, but from the right side, and see what's going to happen. It's going to get really, really big. How big? Well, infinity in this case, right? That's what this sentence right here is telling us. And on the other hand, the end behavior, which is to analyze functions about where are they going for large values of x. So if I plug in something really big, 100, 1,000,000, a zillion, really, really big numbers. So that is. In this case, okay, let me change the colors. And so in this case, as we go really big, what is the y value apparently being hit? Well, it's described by this end behavior notation. So in this, well, it's apparently going to 0, but never actually touching the 0. And on the other hand, likewise, going for negative y values, x values, it's also approaching that y value of 0, but never touching 0. Again, this example is very, very generic, so we will have a better understanding of this without an example that is a little more elaborate. So, something with some shiftings you'll see. All right. Let's move on to that first example. So let's consider the graph right here. So we don't know what f of x is, something weird. We don't care actually. All we want in this case is simply analyze its behavior based on its shape, but more like checking the horizontal and the vertical asymptotes. All right. So number one, we have one vertical asymptote. This vertical asymptote, well, it's a vertical line. It's a vertical imaginary line. And you might want to label that line. So notice this vertical line right here is going through the x value of x equals to 2. And we have two horizontal asymptotes. And well, it's actually possible to have more than one horizontal asymptote, one on top of the other. Not necessarily like like the graph that we did before. I mean, like the horizontal asymptote, only one like this, and only a vertical one like that. No, it's possible to have horizontal asymptotes at different heights, at different locations rather. And a very important note that I typed over here is that, of course, the graph of a function may cross its horizontal asymptote, but it never crosses a vertical asymptote, all right? That's one thing to consider. And we can see that here, this graph is actually, it's crossing its horizontal asymptote, but it's actually never touching the x value where the vertical asymptote is located at, right? So just a distinction in this case. Well, so let's observe this graph. So as x approaches negative infinity, okay, let's see. So it's approaching negative infinity, that is, the graph is going in this direction. What's the value of f of x? Any ideas from the graph? Loud, don't be shy. 2, all right? The value of y equals to 2. All right? Now, in this case, let's focus on the value of negative 2. However, in this case, we are going to approach negative 2. However, this subscript here, which is a negative sign at the top of the number, like it is an exponent, means that we approach from the left in the same way that the plus means that we approach from the right. Okay, so let's see. Let's approach from the left, negative 2 from the left, and well, what's the y value apparently being hit in this case? Where is it going? Negative infinity, all right, negative infinity. What about from the right? Also negative infinity, right? In this case, well, in comparison with the graph we did before for the generic f of x equals 1 over x, from different approaches, one is going to negative infinity, the other one is going to positive infinity. It's pointing towards different infinities from either side. However, there's many cases, there's many graphs in which both infinities are coincident. They go towards the same value. This is something very, very important to keep in mind later when you take calculus 1 when studying limits. In this case, we would say that the limit exists because from either side, the limits are coincident, the values are coincident, and in this case, the limit would not exist because they're going into different direction. But well, again, that's going to be something you will be going more in depth next semester in Calc 2. So again, that's a negative infinity, and in this case, well, for large values of x, in this case for positive values, where is the y value going to? 4. That is this horizontal asymptote, right? So, and that's another example with something a little funkier, something a little less generic than the other example we discussed before. All right. So, yes?
Can you explain how you got 4 on D?
Yes, of course. So in this case, so if we go through the graph, this is what I'm doing. I'm going with large values of x, really, really large values. So notice how the graph is getting close to almost touch the asymptote, but it never touches the asymptote. So, and because 4 is that value, actually, you know what? I should label these asymptotes. Y equals to 4 and y equals to 2. So it's more visual. Okay. So yes, that's one example, a visual example. Well, the most important thing in this case, when it comes to talking about rational functions, well, I'm gonna need some space over here, maybe here. So what happens, for example, if I have f of x equals to 1 over x plus 3? Let's evaluate the function f of x, f of 2. All we have to do, the usual, plug in the value, x equal to 2, whatever you see the letter x, 1 over 2 plus 3, and that's 1/5. All right, well, in this case, we say that the function, this rational function, is defined for x equals to 2. And also, what about f of 0? Well, 1 over 0 plus 3, that's simply 1/3. Well, it's also defined for x equals 0. However, what about, f of, what's this? I'm going to do -3. And that's 1 over -3 plus 3. What are we going to get in the denominator? 0. What's the result of dividing 1 over 0? It's undefined, all right? It's undefined. So here is the issue with rational functions. Here we need to look at all these red flags, rather, which is in this case the set of numbers for which the function is not defined. That is, values of x that output a 0 in the denominator. And well, there is an algebraic process to get that done. You may have seen it before, but still we're going to review from scratch again. But the thing here is that these values of x that output a 0 in the denominator of a rational function are actually the values where we will have vertical asymptotes. That is, values that are restricted from the domain of this rational function. So number one, well, we already had a little visual here of how a vertical asymptote looks like. And well, this picture is from our textbook about how do these vertical asymptotes look like, how in some situations from the left we can go to positive infinity or negative infinity, depending on the graph that we're dealing with, or depending on how the function is set. And from the right, the same story, we can either go to positive infinity or to negative infinity, right? And in the end, well, those are values that the function will never touch. All right? Well, the algebraic process in this case. So number one, it's very important that when we're given a rational function, it has to be reduced to lowest terms. That is, we will have to do some algebra here, some factoring in this case, and in order to get this done. Actually, when finding the vertical asymptotes, those numbers that we obtain about the vertical asymptotes will also constitute the domain. So when we find this asymptotes for these rational functions, I will also write down the domain notation in both, actually, set builder notation and interval notation, of course. And well, there's a little pitfall here. In a situation in which there is a common factor that divides out, well, that one doesn't constitute a vertical asymptote. That's something else. That, in fact, is a whole. And I'm going to talk about this in slow motion, actually. And I'm also going to show you the graph, what's the advantage and the disadvantage of using graphing calculators. And, well, you'll see. Well, so all we have to do is simply Um, to find vertical asymptotes, focus on the denominators. Focus on the denominators, and I'm going to highlight these denominators. What's going on here? Okay, there you go. Because again, this is, if you will, the dangerous part of a rational function. What the critical part that we are going to use to get those asymptotes. So this is all we have to do. All we do is set the denominator equal to 0 and solve the equation. And in this case, well, use every method that you can possibly imagine to factor polynomials. Well, in this case, x squared minus 25. Does anyone identify the form in this case? Don't give me the result of the factor, but rather the form. Yes?
Would be x equals the square root of 25.
X equals, no, I don't mean that the solution, but rather the form, like something squared minus something squared. What's the name of that expression? Yes? It's a difference of squares, all right? So we can factor a difference of squares. Well, x plus something, x minus something, and the something is the number whose square is independent term. That is 25, and the number is 5. 5. That means from here we use the zero product property. X plus 5 equals to 0, and x minus 5 equals to 0. Set the two baby equations equal to 0, solve them, and those values you obtain, negative 5 and 5, are both the equations of the vertical asymptotes. So we will have a vertical dashed line at x equals to negative 5 and another vertical dashed line at x equals 5. Right now we're not going to focus on graphing. That's going to be later in the section. In the meantime, it's just to find the asymptotes. And like I mentioned before, I wanted to use this to describe the domain of this function. So here is how we define it. So I'm going to draw a number line, but I'm going to draw open bubbles at the locations where we will find these two numbers. That is at negative 5 and at positive 5. All right, and in this case, well, we usually shade the number line for all values except where we have these little holes right here. All right, that is at negative 5 and 5. So the one way to describe the domain using the set builder notation, domain, it's x such that x cannot be negative 5 or cannot be 5. That's one way to describe in set builder notation. The other way to describe the domain, which is using interval notation, well, in this case, we need to describe each of these shaded regions using parentheses or brackets, well, depending on the situation. Well, in this case, the fact that we have this arrow pointing to negative infinity, that's telling us that it's coming from negative infinity, and it's going to stop at negative 5. And I'm going to make some mistakes on purpose here to see if you can catch it. If you can catch them actually, then I need to connect with a union symbol to describe this interval. And a third group to describe this last interval. All right, what's my mistake in here? Yes. Brackets. What should we use in this case? Just parentheses, right? So the reason we're supposed to use parentheses in here because of these values that are actually excluded from the domain, all right? In fact, if we had this bracket, well, there's no need for a union symbol in this case. So let's go about changing this to parentheses. And that's how it works. It's important to know the two notations, both the set builder notation and the interval notation. On a quiz, on the homework, on the exam, you may be asked for one particular version, and it's important to know all of them. Let's look at another example. G of x equals to x squared minus 9, and the denominator is 3x squared plus 5x minus 2. So again, it's important to factor everything out to determine whether we may or may not have some common factors that divide out. In those situations, well, you'll see what happens in those situations. Well, it looks like the numerator, again, it's another difference of squares, which can be rewritten as x plus 3 times x minus 3. All right? The denominator, however, it's not a binomial. It's actually a trinomial, 3x squared plus 5x minus 2. And well, so here is the thing. If we had a polynomial like this, let's say, okay, let me make something up. We use a different color just so this is not part of this exercise. Just brief review. If we had x squared plus, let's say, 6x plus, I don't know, 5. All right? The way we factor this polynomial is by what we usually call the double bubble method. So we draw a couple of bubbles, the double bubble, write the x's here, and find factors of 5 that add up to 6. All right? And what are those two factors? 5 and 1, all right, plus 5 and plus 1, right? And that's the factoring of this kind of polynomial. However, it is this easy to factor polynomials when the leading coefficient is 1. However, in our exercise, in exercise B in our notes here, that's a different kind of polynomial. Yes, it's still a trinomial, but the leading coefficient is not 1, so it's not that easy to just go about the double bubble method in this case. All right. Well, there's a few methods to factor this kind of trinomial. And you may have learned a few back in high school, like guess and check. All you do is something like, 3x plus something and maybe x minus something. But that one takes some time to do. And I don't like it. I'm not a huge fan of guessing and check. There's another method called the diamond method. It takes a little while, but for sure it's a more systematic way that, for sure it's going to take you to the final answer after a few steps. I'm going to show you a shortcut for this factoring. So, and well, let me erase this part because it's not part of our notes. Use a different color here. So let me write the polynomial 3x squared plus 5x minus 2. All right, the trick or shortcut I'm going to show you is to, number one, multiply the leading coefficient by the independent term. What's 3 times negative 2? Negative 6. All right, so when we multiply that 3 with a negative 6, that 3 in the leading term disappears for now. So the polynomial becomes like this. That's x squared plus 5x minus 6. Okay? Yes, you'll see what we're going to do, what happened to the 3 and how we're going to retrieve it. What do we have now? We have a polynomial whose leading coefficient is 1, and in this case we can use the easier double bubble method. And while we're looking for factors of negative 6 that add up to 5. What are those factors? Negative 5 and negative 1. So negative 5 and negative 1, that actually is positive 6. So we need a negative. And we need the addition to be a positive. So any other ideas? The numbers are correct. All we need is to tweak the signs in here.
The negative 1 to a positive 1.
Positive 5, right? Okay, what about the 3? So
Positive 6.
Mm-hmm. Positive 6. Oh, yeah, positive 6. Positive 6. Yes, 6 times negative. Yeah. All right. So here is the thing. At the beginning of the problem, we multiplied by 3. We need to undo this operation so we are still even with the expression. That is, at the beginning, again, we multiplied by 3. Let's divide by 3 in this case. Okay? So, If possible, divide out 6 over 3. That's going to output x plus 2. And whenever it's not possible, like in this case, x minus 1/3, this is what we're going to do. We're going to move this 3 to be the coefficient of the x right here, 3x minus 1. And that's how the trick works. Instead of doing the guess and check, which may take a while, or it may work for some of you, so what I'm trying to say here is do the method that you prefer. It will be fine, all right? So let's go back to our exercise in here. And so that's going to be 3x plus 1 times x plus 2, or the other way, it doesn't matter. It's multiplication, so the order doesn't really matter. And that's our rational function in factor form, in reduced form. Well, reduced-ish, because nothing cancels. And in this case, well, we care about the denominator. That's the part, oh, come on. Yes. That's the part that we will set equal to 0. That is 3x plus 1 equals to 0, and x plus 2 equals to 0. So this is x equals to negative 2, and this is 3x equals to negative 1, and x equals to negative 1/3. So those are the equations of the vertical asymptotes in this case. All right, that is, if we were to graph this function, we will see those imaginary lines, or we will have to, well, if we do it by hand, we will have to draw dashed lines at x equals to negative 1/3, and another one at x equals to negative 2. All right. So let's see what's next. Oh, actually, this one's supposed to be negative. This becomes positive because of this negative here, right? Silly sign mistake. So, stating the domain, x such that x cannot be negative 2 and cannot be 1/3. That's the set builder notation, and in interval notation, in a similar way that we did before, this is negative infinity to negative 2, union negative 2, 1/3, and union 1/3 to positive infinity, which corresponds to the open bubbles that on the number line that represent the vertical asymptotes in this case. All right, let's look at one more example. X squared over x squared plus 9. And again, all we have to worry about is the denominator when it comes to finding equations of vertical asymptotes. That is, let me highlight, x squared plus 9. I'm going to set it on the side. X squared plus 9 equals to 0. And you'll see what's going to happen in this situation. Well, x squared equals to negative 9, and x equals plus or minus the square root of negative 9. And what's the square root of negative 9? Any ideas? Not undefined. Plus or minus 3i, right? In this case, we have imaginary numbers. X plus or minus 3i. Well, in this case, since the equation in the that comes from setting the denominator equal to 0 does not have real solutions, because we only care about real solutions. We're not looking at the field of complex numbers, only real numbers. So in this case, give me 1 second. No real solutions. No real solutions, and therefore no vertical asymptotes. No vertical asymptotes, and therefore the domain will be x such that x belongs to the set of all real numbers. That's the fancy way to write all real numbers as set builder notation, but of course using Interval notation, negative infinity to positive infinity. So yes, question?
Is I equal to the square root of negative 1?
The square root of negative 1, exactly. That's what gives rise to the imaginary numbers. And well, in this case, we're only caring about real numbers only, no imaginary numbers at all. All right? So that's one more example about it. And let's look at, yes, we're going to have time for the last one. So first of all, again, every time we have a rational function, let's factor every single polynomial that you see in both numerator and the denominator. Because it's possible that some weird things happen. So let's see. Factors of 6 that add up to 5. What are those factors? Any ideas? Plus 3, plus 2. And x plus 3 in the denominator. And here is the thing. Check this out. These two cancel out. And we are left with r of x equals to simply x plus 2. What kind of function is that one? It's a linear function with a slope equals to 1, rise 1, run 1, rise 1, run 1, etc. And what's the 2 representing here? Shift up to units, right? Or the y-intercept. That's also what it represents. Well, let's draw the graph. Why not? I mean, how hard would it be to graph x plus 2? I mean, and what could go wrong about it? So go up to units, rise 1, run 1, rise 1, run 1. And this is the equation of the line that we would obtain, all right? I mean, also, nope. Let me go to window or no, mode. Function, y. And what do we have? Okay, let me open parentheses. That's x squared plus 5x plus 6. Close parentheses and divide by x plus, x plus 3. And let's see the graph. And for some reason, we're not able to see the graph because some 6 standard. And that's our linear function, right? However, okay, so here's the thing. Calculators, graphing calculators are very smart devices. However, they're not that smart because in this particular case, there's something that this graphing calculator is not showing us. What's that? Well, this factor that was divided out, this one right here, set it equal to 0 still. X plus 3 equals to 0, x equals to negative 3. If we did the usual process, well, we would think that there would be a vertical asymptote here at x equals to negative 3. However, it's not a vertical asymptote what we're going to have because the graphing calculator is not showing, graphs before and after some particular value of x. It's just showing us a linear function. So in this case, this is the location of, in this case, of a hole. So let me draw a hole in here and there and complete the graph. And that's what graphing calculators don't show us in this case. So we need to be very, very careful about reading graphing calculators because they're not going to show us some of the most important aspects in here. Let me make a small change in the rational function I typed in the graphing calculator so I can show you more specifics here. Let me change this 6, I don't know, with a 9, for example. So it doesn't cancel anything and graph. Well, in this case, we can actually see a couple kinds of of asymptotes. In this case, we're going to have some sort of a slant asymptote. It's a dashed line that has a slope, that has some inclination, and we also have a vertical asymptote here. However, again, here is where we need to be careful when relying fully on graphing calculators, because they're not going to show us everything. They're not showing us those dashed lines that describe the vertical asymptotes, all right? And that being said,